conjugated molecule, including the hapten. Now, as soon as the hapten is recognized as part of that conjugated molecule, it may also be recognized in its individual state. So prior to conjugation, they can't be recognized at all. After conjugation, they can be recognized in their conjugated state and in their individual state. Most of the time, these haptens are associated with types of allergies like pollen, or I believe some people have dust allergies. It's very small particles that aren't associated with specific pathogens. They're not cellular or viral. There's other sorts of molecules. Now, antibodies are what bind to our antigens to produce an immune effect. Dusting off my keyboard here. And up in the corner here, we'll just go over a little bit of this antibody structure before we delve into their function. An antibody generally is composed of two identical heavy chains. You can see these highlighted in purple here, and the ribbon structure here on the right also shows our two heavy chains and our two light chains, which are also identical to one another. Every antibody contains a F sub C region, which is also our constant region, and a region that is specific to binding for antigens. These areas here, each chain is combined or linked to the other chains in the structure by disulfide bonds. And you have a constant and variable regions. So regions that are always the same regardless of the antibody, and regions that change up depending on the antigen they want to target. This is the Fab region here on top. It stands for fragment of antigen bonding. And that's what it's made up of our two arms of the Y structure. And on the very far end of the Fab region is the actual variable region where the changes occur, where specific binding to antigens happens. And this is the area that's responsible for neutralization of antigens, binding to prevent functioning or agglutination slash aggregation. Those are two words for the same thing. Just essentially just the balling up, the binding, the cross-linking of different antigens to make them more recognizable to the larger immune system. Antibodies belong to a handful of different classes determined by the nature of their constant region, so the nature of this piece down here, just the bottoms of these chains. And each class is belonging to a certain isotype. The main differences between each class are involved in their availability, meaning where do they act in the body, where are you likely to find them, also how many of them are produced, how available are they to be used, defined also by their function, what type of pathogens do they target, how do they exert their antigen neutralization effect, defined also by size and arrangement, and body size, like I said. So where do they act and why? The most abundant type of antibody is the IgG. It's the most abundant. It's able to penetrate tissues, get pretty deep into the body when infections persist beyond the surface level. And they're also the only class of antibody that's able to penetrate the placental barrier, and it confers passive immunity to a developing fetus within the mother. It's also the most versatile. So it's the most able to change up its individual function to target new antigens that are arriving in the body, more so than others, which are more attuned to specific classes of pathogens, which then differentiate to become, again, more specific as a specific immune response. IgG, these G immunoglobulins, have just the highest ability to differentiate very specifically to specific pathogens. For the M immunoglobulin, we are here talking about antigen binders for specifically B cells, which operate by forming a pentameric unit, which leaves us with a total of 10 Fab sites. So if you think back to the Y shape with